few weeks ago, I read this fascinating paper. I thought, we've got to get this author to give a talk here. So we made an invitation, and here she is. Dr. Bastani did her PhD at Stanford, and then spent a year as a postdoc at IBM. And then graduated from Harvard in physics. Interesting. Her research involves machine learning algorithms for data-driven decision-making with applications to healthcare operations, social good, and revenue management. She designs methods for sequential decision-making, like bandits and RL and active learning, and leveraging auxiliary data, like transfer learning and meta learning. And recent applications include deploying a targeted COVID-19 testing strategy in Greece, speeding up clinical trials by leveraging surrogate outcomes, meta dynamic pricing across multiple related projects, and predictive analytics with small data. She does many other activities, but today she's going to talk about COVID-related stuff. So I'll stop introducing her and let her describe her work. Looking forward to it. Thank you.
Thank you so much, Russ, Neeraj, and Sabina. Let me quickly try to share my screen. Can everyone see this? Awesome. Yes, so like Sabina said, please interrupt me if you have any questions. I'm really terrible, as I've learned from teaching, at monitoring the Zoom chat online. So please just interrupt me, and that would probably be, and I'd love to keep it as interactive as possible. So again, like, I'm Hamsa. This is joint work with a couple key perpetrators, so Kimon Drakopoulos and Vishal Gupta from USC, and John Lachogiannis, who was our software architect who helped us design and deploy this tool on the ground. And this is largely a collaboration with the Greek government. So the remaining co-authors are all members of the Greek COVID-19 Executive Committee. So they're public health experts and epidemiologists who obviously were instrumental to actually getting this deployed. So just to give a brief outline about what I'll be talking about, and feel free to interrupt me if you want to dig into details in certain parts or skip over certain parts. But I'll overview the Greek context and the deployment, and then I'll talk a little bit about the tool that we deployed called AVA. So it's a design, algorithmic, and statistical challenges. And then I'll talk about some counterfactuals we did on how effective it was and whether it worked. And then if there's time, I'll end with a couple concerns about using publicly available data for COVID, which I think is still pretty relevant going forward, given the continued number of cases that we are seeing for international travel. So when we joined this project, it was about around April or May of 2020. So if you guys recall, if you take a little memory jump back, we kind of started realizing that COVID was a big issue around February 2020. And Greece kind of followed a very conservative approach. They went into a very stringent lockdown. And so when we were talking to them, they really had no cases, or very, very few cases. But as they were approaching that first summer after COVID had hit, they were getting pretty nervous because tourism, believe it or not, is a big chunk of Greece's GDP. It's 25%. So a lot of the economic activity kind of relies on it. And so they really had to open up their borders to non-essential travel in order to get economic activity up again. So when we were talking to them, they'd already decided that on July 1st, 2020, they were going to open up their borders. But obviously they were very worried about the public health consequences. So they were worried specifically about bringing in a lot of positive cases in the form of infected but asymptomatic travelers from other countries. And the best case scenario that you could do at this point is to test every traveler who is coming into the country, see if they're positive or negative. If they're positive, you ask them to self-isolate for a while. If they're negative, you say, come on in, spend as much money as you can because our economy needs it. But unfortunately, at this time, we didn't have rapid testing kits. We didn't have vaccinations. It was very difficult to get a test at this time because everyone was relying on RT-PCR testing. And the supply chains for that were just very inelastic and could not be easily expanded because every country was trying to get its hands on more PCR testing capabilities. And so it just wasn't possible to test every arriving traveler. But what they could do do was test a subset of them. So what we proposed was sort of the next best thing. We said, why don't you just try to predict who is likely to test positive and preferentially test those individuals, because then you're kind of getting the best bang for your buck. You're going to catch the most positive cases at the border, given a limited, a budget constraint on the number that you can test. So that's exactly what our tool AVA does. It's a real-time data-driven system that allocates limited testing resources to primarily just recommend who to test. And as a consequence of some of the infrastructure and the risk estimates that we built for this tool, we are also able to advise the Prime Minister's office on which countries to gray list. So gray listing is this procedure where Greece will determine that a particular country is sending in too many risky travelers, and so they will require a negative PCR pre-test for all passengers who are arriving from that location within the last 72 hours of entering the border. So obviously, if we could gray list everyone, then things would be great in terms of public health. But this is actually a very costly hammer, both politically and economically. And so they really, really didn't want to do this. So when we looked at some of the data that we collected, we saw that arrivals, for example, dropped by 40% when we gray listed a country. Because again, at this time, it was very difficult and inconvenient to get a test done. So it's not like the current climate. And on top of that, it kind of affected Greece's relations with that country. So it was something that kind of was only done when necessary. And the other piece that went into this is that we were able to give some interpretable insights on domestic decisions to the Greek government. So for example, if we see a large inflow of likely infected tourists to certain parts of Greece, they can mobilize mobile testing teams or issue like ad hoc orders to do social distancing or masking mandates and so on. Questions at this point? Cool. So this is roughly how AVA flows. So we have about 30 to 100,000 passengers who arrive every day during peak summer season. This is actually very low for Greece. So these are pandemic numbers. So they come through air, water, or land. 24 hours prior to travel, we have families fill out something called a passenger locator form. So travelers basically report where they're coming from, some demographic information, where they're going within Greece, and some contact information. So basically, this is how we collect features. And the primary feature we'll be using is where they're coming from, because that's what we found to be very predictive of whether or not they're likely to test positive while abiding by GDPR like privacy constraints. So this all gets fed into our system AVA. And then, like I said, testing resources were pretty scarce, so we can't test most people, unfortunately. So passengers get sent a QR code based on our tool, and a subset of these passengers will be selected to be tested. And so these guys jump behind one of these curtains. They get this sample taken from their swab, and then that gets linked to the QR code scan and then gets shipped off to a lab. Each port of entry has contracted with a specific lab, and so they've committed to returning those test results within 24 to 48 hours, and that gets fed back into our system. So the key behind what makes AVA work is this dynamic feedback loop here. So basically, we make a set of testing allocations, and then by predicting who is likely to test positive, essentially, and then we actually collect testing results actively from those people. Those get fed back into our system in order to update those predictive models to make the next set of allocations. So anyone who has been in the pandemic will tell you that the pandemic is highly non-stationary, so there were risk was spiking and settling back down in various locations throughout that summer. And so being agile and responding to the current status of the pandemic in this way was kind of, I think, very necessary in order to make efficient allocations. Questions so far? Cool. So the operations of this was fairly large. So there are about 40 points of entry that feed into Greece based on, again, air, water, or land. There are about 400 medical professionals and 300 border agents that were actually staffing the supply chain, 32 labs at every point of entry contracted with, and then eventually all of that fed into a dashboard for various policymakers, particularly the COVID-19 Executive Committee, with whom we met every few days to kind of discuss both domestic and the international decision-making with respect to COVID. So things like gray listing countries and so on. This is actually the Greek Prime Minister, and this is my co-author, Kimon Drakopoulos. So Kimon was Greek, and he actually went to Greece in order to enable this communication channel, which was invaluable for this project. Okay, are there any questions about the setting? If not, I will jump into the mathematical part.
Well, it might be the next slide, but do you have an explicit objective function, cost function? Is that coming right now?
Yes, that is exactly. Yeah.
Right here. Thank you.
So there are a couple of objectives, like I mentioned, but the primary objective in terms of the math and the algorithm we're focusing on is just being able to catch the most infections. So before I formalize this, let me just give a little bit of notation. So passengers were basically thinking of the primary feature of where they're coming from, their origin location, which is a categorical variable. So we're going to segment passengers into basically discrete types based on their location. For now, you can think of this as their country, but actually we do something a little bit more adaptive using Lasso, which I'll talk about later, to take into account more granular location information like their city. But basically, you can think of these discrete type passengers. So their type K passenger will have a test outcome that's a Bernoulli random variable around some risk metric RKFT. So this risk depends on both the time step, because the pandemic is non-stationary, and also their type. And this is an unknown quantity. And the decision we're making are the number of passengers that we want to test, NKE of T. So basically type K passengers, how many of type K passengers at every entry on every day. And so if you just put this together, if we want to maximize the expected number of infections caught, it's this very simple objective function. It's just a number of tests that I'm allocating to a particular passenger type times the expected probability they're going to test positive, summed over all the entries, summed over all the types, and summed over all the days in the summer. So if I knew RKFT, this would be a trivial problem. I'm just going to figure out, look at who is the riskiest passenger, and I'm just going to allocate my tests greedily until I run out of tests, and then that's it. But unfortunately, we don't know RKFT, and this problem is actually endogenous. We actually, our estimate, our hat KFT depends on recent testing allocation. So let's say that I didn't test any Spanish people because I thought they're really safe. Then tomorrow, if they become risky, I won't actually have any data to even figure out that they are risky. And other than this, we also have to respect some constraints. So like I said, every point of entry contracts with a particular lab. And so it has its own testing budget constraints. So some labs have more testing budgets than other labs. Some labs are contracting with multiple points of entry and so on. And we also cannot test more than the number of arrivals for a given type. So if a type looks really risky, we can't really test more than the number that actually show up to the border. So there's also no shows, which is another piece of this. So people might fill out a passenger locator form, but then not actually show up to the border. Okay, questions? Cool. So let me first talk about.
I had a question. How does this work in terms of families? Because it seems like if you have a group of 5, if you test one of them, you probably want to quarantine the whole family until you get that test back. And you probably don't want to test all 5 of them. It probably makes sense to test just one.
That's exactly how it works. And that wasn't even a choice. That's an operational constraint. So the family fills out a passenger locator form. And then once they fill it out, anyone in the family, they get to choose like who gets tested, because typically they don't want their child to be tested or something like that, or an older member of the family. And if they test positive, when any member tests positive, then that whole group has to self-isolate. Does that answer your question?
And then your only actions are test or not test. You can't say, oh, this family is particularly risky. I want them to stick around for 3 days when we get more tests. It's just you either stop them and test them, or you let them through.
Exactly. That goes to the contact tracing team. So the contact tracing team, so we only have half the testing budget of the country. The other half of the testing budget belongs to the contact tracing team and also the mobile domestic teams. So if they think that a particular family is risky for some reason, then they will follow up with them based on exposure. Probably it's because they've been exposed to some other family that tested positive, right? Great question.
I'm probably getting ahead, so feel free to postpone, but are you going to compare to other ports of entry that don't use your method? it seems like that would be hard to compare and figure out how well how well EVA is working.
There are no points of entry that didn't use our method. So it was deployed nationally. What we do though is, because this is an algorithmic strategy that has a lot of exploration, we're going to use a bandit method. It turns out that we can just use inverse propensity weighting. There's no unobserved confounders because it just follows the algorithmic strategy. So we know the exact propensities in which the algorithm will test a particular individual. So we just use inverse propensity weighting to compute counterfactual performance.
Okay, awesome. Thank you.
Yeah, thank you. Cool. So I'm going to talk a little bit about how we actually allocated the test. So the sort of bandit part, and then I'll switch over to some of the estimation part later. But please interrupt me if you have any questions. So as most of you have probably guessed, there's an exploration exploitation trade-off here. So on one hand, we want to make sure that we are testing enough passengers from every type so that we actually know whether passengers of those types are risky or not. Basically, if we are not surveilling every type, then there's a risk that a particular location might start spiking and we won't even know that that happened. This is also kind of useful for the downstream gray listing decision, so that basically we're keeping tabs on any location that's looking especially risky in case the Prime Minister's office wants to gray list them. But ultimately, our goal is to do exploitation, right? We want to use most of our testing budget to test the riskiest types so that we can catch the most positive cases and quarantine them so that they're not running around partying and spreading the infections among the general population. So exploration exploitation, there's tons of popular solutions. It dates back to, I think, Thomson sampling by Thomson in 1933, but there's also upper confidence bound. There's the Gittins index, which is sort of the optimal dynamic programming solution, but is sort of intractable. We'll be building off of the Gittins index, but with a tractable heuristic. So before I jump into which particular algorithm we use, let me just preview like what a bandit algorithm might do here. Let's say that we have Spanish people and German people, so that's ES and DE. We have some estimate of their prevalence. So these are the point estimates, and then we have these 95% confidence intervals. So you might look at this and say, well, Spanish people look a little riskier than Germans based on their point estimate, but I'm really not sure because my confidence interval for Germany is huge. So it's possible that German people are riskier or even much riskier. So a bandit algorithm will typically at this point say, let's be optimistic, or let's do some exploration. And so it'll test a German passenger. Then I get the test result back and I get to update my posterior, and you can see that this confidence interval has shrunk and then point estimate has also shifted a bit. Now I'm pretty sure Spanish passengers are riskier than German passengers, so it'll switch to exploitation. And so we'll start allocating our tests to Spanish passengers. We get that result back, we update our posterior, and so on. So this is kind of the ideal scenario in which a classic off-the-shelf bandit algorithm would proceed. We use something called the optimistic Gittins index. So this is just a one-step look-ahead approximation of that optimal dynamic programming solution. So typically, these bandit algorithms, there are a lot of asymptotic heuristics that work well when you have large horizons, but we have a small horizon, so we want to make sure that those constants are tuned as well as possible. But it actually doesn't really matter which algorithm you use here, like fundamentally something that trades off exploitation and exploration. The nice thing about the Gittins index algorithm is that it's very easy to explain to policymakers. So it doesn't have any of that stochastic sampling that Thomson sampling has, or the high dimensional ellipsoid that UCB has. You have an index, all the complexity is shoved into that computation of the index, and then you just greedily pull the arm that has the highest index. So it's a little bit like UCB in that way. And then you update your posterior based on whatever observed result in the index. And then, when you're explaining this to a policymaker, they love it because it's deterministic and it feels greedy, even though it's not greedy because exploration is baked into the index. So there are a couple of challenges here that make running the off-the-shelf algorithm not straightforward. So the first thing is actually simple. The dynamics that are reward functions of how risky different locations are non-stationary. So it's not like we want to use data that's like 1 month old to figure out whether a particular passenger is risky. That's probably too stale. So based on conversations with the epidemiologists, we decided to discard any testing results that were over 2 weeks old. So this created issues because the problem that we have is also batched and suffers delayed feedback. So batch decision-making says that instead of this ideal scenario where I test a passenger, I get their result back, and then I test the next passenger, I get the passenger manifest at the start of the day, and I have to make all my testing allocations at the start of the day. And the reason they did this was really an operational constraint. In Greece, lots of places don't have very good internet connection. So they didn't want people getting emailed QR codes in real time and then possibly pooling up in the airport if the internet connection becomes unstable and then, infecting each other. So that would actually be worse than making inefficient testing allocations. And so we took the whole batch, for each batch is a day. We took the passenger manifest for the entire day, made all the allocations up front for that day. But even if we could do it in real time, it wouldn't be that useful because obviously we have delayed feedback here. So it's not like I allocate a test and I immediately see the result. It takes about 48 hours to get that shipped to the lab and for the lab to actually do the test and report it back into the database. So these two issues are what causes the problem. And then finally, we also have constraints on budgets and so on. So let me just try to illustrate what happens in a given batch if we try to just run the naive off-the-shelf algorithm. So let's say we have 4 different types of passengers, and I've computed the optimistic Gittins index for every type. So clearly, again, we just test the type with the highest index. So we'll go for type 1, and we allocate a test. Unfortunately, once we allocate a test, nothing happens, right? Because we don't get the results back until 2 days from now. And I'm just doing this in my on the computer or on the server. There's no actual dynamics that are actually happening on the ground yet. So if the algorithm just ran like this, it would just keep testing type 1 passengers until we ran out, and then type 3 passengers until we ran out, and so on. So it would overexplore one or a handful of types while we're waiting for the testing results. And you might say, well, that's only a 3-day problem because 1 day for the batch to finish, 2 days for the results to come back. But because the problem is non-stationary, our data is only useful in a 14-day window. So this is actually a huge chunk of the time horizon. And so there is a literature that's kind of gone on batch bandits that kind of looks at this typically for online platforms. Unfortunately, none of these algorithms work in a non-stationary setting to the best of our knowledge. So they all follow these like explore then commit strategies where early exploration batches kind of uniformly experiment across all the arms. Then they kind of find a winner and then they exploit that arm for the rest of the horizon. But again, you can't do this in a non-stationary environment because we're constantly discarding those exploration batches, right? Because after 14 days, anything that I did before to explore is not useful anymore. And so I need to keep on exploring continuously. So we really need to think about how to weave in exploration and exploitation within the same batch, even though we are getting this delayed feedback is essentially the problem. So we came up with a very simple trick for doing this. We basically just simulate the when we allocate a test, we know that it's going to reduce the uncertainty. So the problem is that I've allocated a test, I know it's in the pipeline, I know it's going to reduce the variance of my estimator, but it hasn't yet reduced the variance of the estimator. And so we're just going to simulate the expected reduction in the variance. And this is a very simple computation. Let's say we have a beta distribution with alpha k successes and beta k failures. When we allocate a test, I'm just going to add 1 expected success and 1 expected failure to that posterior distribution. And that basically has the feature of keeping the mean the same because I don't really know any better than the current mean, but it reduces the variance by 1 expected test, which is kind of what we want. We don't want to keep exploring an arm if we've already allocated them 100 tests. It's just that we won't hear back for 3 days. So I'm going to call these pseudo Gittins indices because they're not real Gittins indices. They're based on these fake tests that we haven't actually gotten back yet. But they have this nice feature that they dynamically update. So now if I go back to my picture and I allocate a test to a type 1 passenger, then we do a certainty equivalent update. You can see that the index actually goes down. So the index will always go down because the mean doesn't change, but the variance always reduces. And then we'll move on to a type 3 passenger. So hopefully what this does is it allocates the estimated number of tests that we actually need to resolve uncertainty for any types that have high variance. And then all of the remaining tests get allocated to types that have high mean. And that's the exploitation part. So ultimately, this is what we want any bandit algorithm to do. We want to do the minimum required for exploration for every type, and then we want to exploit all the way with the remaining tests. So you don't have to believe me. You can just look at the data. So this is actual data that we had for arrivals and testing within a given batch. So one day in which we were running the algorithm. Because it's real data, unfortunately, I had to anonymize everything. So sorry about that. But oops, sorry. But what we have here is basically on the x-axis, we have different types. So these are either countries or cities, and they're ordered from high to low risk based on our prevalence estimates. So you can see that why tourism is even feasible. Most types have low risk. This is actually by construction, because if a large type, if a high arrival type had high risk, we would gray list them or they wouldn't be allowed into the country. So for example, the US wasn't allowed because they would probably be here and they would probably be a large bar. The bar itself is a number of arrivals, and the teal portion is the number of people we're testing, and the pink portion is the number of people we're not testing. So you can see exploitation here, we're basically testing 100% of all high-risk arrivals. And you see exploration in that we test a non-zero fraction of every possible type across the board, and that's the surveillance or exploration part. Questions?
Yeah. Do we know how many were positive tests?
Within this?
Yes. I guess for the greens,
yes.
you can see immediately. For the pinks, you might find out a week later that in fact they were infected. And so you can now revise that. So you have both green and both teal and pink. Do you have the actual statistics of what percentage actually were positive?
Yes, that's in the X. So these are ordered by the statistics on what percentage were positive. So we have an empirical based method. I'll show you that plot in a little bit. That has the risk estimates. Yeah.
Okay. Not the estimates, the actual statistics, but that'll come later on.
Right. Well, I can't show you the actual numbers, but we open source the data set. So I guess you can see them if you download it.
Okay.
But okay, I guess the average statistic is that at the start of the summer, it was like 2 in 1,000 that were testing positive, and then it went a little bit higher later on. That's if you did a random sample. In our sample, because we're doing a bandit strategy, we got a little bit more bang for our buck, so it was about 85% higher than that. But these guys that are on the high risk end, they're about, they have the worst possible likelihood of high risk is about 0.05 people testing positive. Sorry, 0.5%. So 5 in 1,000 people testing positive. That's when we trigger the gray listing action. And then if that country has special relationships with Greece, they can try to evade getting gray listed, but typically the arrivals and the prevalence will start dropping from there because there's some sort of political discourse. And then the ones all the way at the end here, they're more like 1 in 1,000.
Again, even the pink, you might find out later on that these people actually did have COVID, because you find out downstream.
Yes, but the teal is a random sample of the entire bar, so it should concentrate reasonably.
Okay, good, thank you.
Yeah.
Cool.
Okay, great. So the other thing that I didn't mention is the testing constraints. So this is a map of Greece. As you already know, Greece is a whole bunch of islands. And so they have lots of different points of entry. We're not particularly creative. So airports are airplanes, and seaports are anchors, and land ports are cars. And some points of entries are hidden due to national security reasons, or that's what they told us. Blue basically means that we have a lot of tests per arrival. So like every point of entry, again, is contracted with a different lab, and that lab has a different capacity based on their staffing and their PCR testing machines, and whether or not they're using dry swabs and wet swabs and things like that. And so if it's a very red point of entry, that actually means that they have very few tests per arrival. And Greece was very adamant about not changing their contracts over time based on arrivals. And so you can see some weird things, like this airport has very few tests per arrival, and this seaport has a lot of tests per arrival. So even though they're right next to each other, so you can imagine they could do some pooling or budget sharing, but they were not willing to do that because of the additional complexity. So it just is what it is. But what matters is also like the types of passengers, right? Like who is coming where. So like, for example, if you wanted to test a German, That was really easy. Germans arrived in huge numbers. So Germany is DE. Dark red means large numbers. So they arrived in huge numbers kind of across any point of entry. So if you want to test a German, you pick them up at any one of these points of entry. But let's say you want to test a Northern Macedonian, that's MK. They don't really arrive at most points of entry. They only come in through land. And they also come in pretty small numbers. So if you want to test a Northern Macedonian, you better hope that you save testing budget at those particular points of entry. So this creates some sort of a trade-off that you don't want to use up testing budget on common types at points of entry that serve rare types. The bandit algorithm so far that we've talked about doesn't really think about this at all. It just kind of says we choose the type with the highest pseudo index and we find a passenger to test. But where we find that passenger, which point of entry actually does matter. So Shipra, Nickel, and some other people in the bandit community have come up with these nice LP-based bandit algorithms that deal with these sorts of constraints. But we actually didn't know how to integrate that with our sort of batched our batched bandit approach of doing these certainty equivalent updates. That seemed to become a combinatorial problem that we couldn't solve in a tractable way. And so we just implemented a really simple greedy heuristic, but probably there's some smarter thing we could do here. But basically when we want to test a passenger from a particular type K, we just choose the point of entry that has the most remaining tests available. So this is almost like a submodular heuristic. We're thinking, you know, if there's lots of tests available at a particular location, hopefully we're going to save tests for those unique types and more constrained ports. So let me just show you how the algorithm proceeds on any given batch. This is extremely computationally fast and simple, which it had to be because we only had about 2 minutes to run this by the time we got the passenger manifest, and then the first flight landed of that day to send the QR codes to these people. And it turns out that AWS servers are incredibly slow at emailing QR codes. So that was sort of the bottleneck. So this had to go quickly. But basically we get the passenger manifest at each port. We get the port specific testing constraints, and then we have all the historical testing results. So the first thing we do is we compute the Giddens indices. We do any updates for pending tests that we've asked for in the last 2 days, but we haven't gotten back yet. So we get two simple tables. One is for every type, we get that pseudo Giddens index. And the other one is the passenger manifest. For every type, we have the passenger ID, the port that they're coming to, and how many remaining tests are at that point of entry. So first thing I do is I look for the type that has the highest pseudo Giddens index. I say, type 2 passengers. So I find all the type 2 passengers on my passenger manifest. I see one is showing up at port 1, the other one's showing up at port 3. Port 1 has a lot more tests than port 3. It has 500 tests. So I'm going to take the port 1 passenger. So I just cross them off my passenger manifest. I do a pseudo update here. And now I see that type 1 passengers have the highest index. So I see that type 1 passenger is only arriving at port 3. So good thing, you know, I didn't waste my port 3 test on a type 2 passenger. Right? And we just keep going until we run out of tests or we run out of passengers, usually because we run out of tests. Questions about how the algorithm works? Cool. So I've been weirdly quiet about how we actually do the prevalence estimation or the risk estimation. So there are two issues here. One is, like Russ mentioned, we have imbalanced data. So very few people actually test positive. And this obviously creates statistical challenges in terms of being able to get the mean right. So the real question we're doing is really risky countries have 1% testing positive, and we're trying to distinguish these guys from the 0.1% who are safe, right? And the problem when you have imbalanced data is that you can do really well by just always predicting 0, right? So if only 1 in 1,000 people test positive, if you predict 0 for everyone, you already get 99.9% accuracy for free. So we want to do better than that because that's completely useless from a decision-making perspective. And then the other thing is that we have high dimensional features. So even though we're only dealing with origin location, because it's a categorical variable, it has 17,000 levels because there are 17,000 cities in any 2-week period that we're looking at. And there are about 170 countries. So if we do the country level types, then we get very little variance because there's very few types, but we're going to incorporate some bias. So for example, at this time, New York City was way riskier than the rest of the United States. So lumping in New York City with all of the US is obviously costing us something in terms of efficiency. So we'll interpolate this using Lasso. So for the first part, what we did was we used an empirical Bayes approach. So we basically assumed that every country's risk was sampled from a shared prior, which was a beta distribution, because we are looking at Bernoulli outcomes. And what this was actually turned out to be pretty nice. So again, I'm going to compare to the zero estimator, because again, the zero estimator does really well just trivially. And you can see that if you don't regularize your estimate at all, then it actually does far worse than the zero estimator. It's actually not even pictured on this plot, but it gets very high mean squared error. So this, we're evaluating mean squared error in a held out test set from historical data. And then you can see that as we strengthen the prior, the mean squared error minimizing point is something down here. It actually does better than that trivial zero estimator. And what we actually implement is a very simple moment matching method that runs really quickly and has a simple closed form. So that's this red point. And you can see that it's basically mean squared error minimizing, but it's much more stable, which has nice properties for policymakers because they freak out if the estimates kind of jump up and down. Questions about this? Great. So this is kind of what our results look like. So we show them on a dashboard every day. So these are the same types that I showed you before from high risk to low risk, but now I'm showing you the prevalence estimates from the empirical Bayes estimator, as well as the 95% confidence intervals. So you can see that we actually get pretty decent control over the confidence intervals, even though we're throwing away data that's more than 2 weeks old, and we only have 1 in 1,000 people testing positive. And then the other issue that I mentioned is this type granularity. So what we're going to do is we're going to identify most types at the country level, but we want to isolate very risky cities like New York City because we don't want to lump that with the US. So we just use Lasso to identify a sparse subset of cities that are particularly risky beyond the country that they're coming from. So to show you in a picture what this would look like, let's say that my last 2 weeks of data, I have this particular country and I have 7 different cities from which people are showing up. And I look at recent historical testing results and I see like all of the risks kind of hover at 2, except for this blue bar here that seems to be more like a 5. If I put this into a lasso regression with indicator variables for each location and I look at the support that gets picked up, typically it'll be something like none of these indicators will get picked up in the support except for this one blue country. So that means blue city, sorry. So basically this would be like New York City getting picked out. So and this is the rest of the US. So then we'll have 2 types for the US. We'll have New York City, US, and then rest of US, right? And so in this way, we dice up countries that have especially risky cities, but for the most part, I think we had 170 different countries that we were getting tests from, and then we had maybe an extra 30 that we would get picked up from this lasso. So nowhere even close to the 17,000 cities that we would have if we just didn't run this procedure. Any questions about the algorithm before I jump into the evaluation?
Did you ever have cities that were much better, and hence you would look at everyone from a given country except for that city to go both ways?
So we do see cities that are much better, but we don't define new types for them because every time we define a new type, it becomes an arm. And so the bandit will explore that arm. So if it's safe, we don't want to waste tests on doing that because we only get high reward if it's a risky city. So yeah.
Your options are either use a whole country or ignore most of the country, but use a city, but you don't go the other way.
Exactly. Yeah.
I understand why. Cool.
Cool. So after we finished running this tool, we had to quantify the effects of ABA. If you work with policymakers, they really want to know what bang they got for their buck. And so here we were in a lucky position that, so usually with bandits, it's a little bit difficult to do policy evaluation because often you stop exploring and you start exploiting. And so your inverse propensity weights don't behave well. But here it's not a problem because this was a highly non-stationary setting. So we ended up doing a lot of random testing or exploration throughout the entire summer. And so the inverse propensity weights behave really well. And so we can compute counterfactuals on how well other policies would have performed. So the first thing we compare to is random testing. So random testing is very attractive for policymakers because that was basically what they were going to do before we stepped in, because you don't need any infrastructure. There's no financial investment. There's no database, right? You just pull random people off of the customs line. It's kind of like the TSA pre-check, or supposedly what the TSA pre-check is doing. Not pre-check, sorry, the TSA security. And so what we did was we just used inverse propensity weighting to try to figure out how random would have performed. So this red line here is what we did, and this teal line is what random would have done. And so we see that we split it up into the peak season and the off-peak season. So in the peak season, we got a lot more arrivals before kind of the end of before October started. And then in off-peak season, there's fewer tourist arrivals, so we're able to test more people. And so in the peak season, we see about an 85% increase in the number of infections that we're catching at the border compared to what random would have done. So just to put this in context, we had about 7,500 tests at the border. We would have needed 14,000 if we used random to catch the same number of infections, which incidentally was the testing budget of the entire country at that point in time. So it was just infeasible to do that. And the reason that it gets worse in off-peak is because it really depends on the percentage of people that we're testing. So targeting is really only effective if you have scarce resources. So in the limit where you're testing everybody, any policy is going to do exactly the same, right? And so what we see is, so here we're holding the number of tests constant, but the arrivals are changing. And so you can see that when we get to test a very small percentage, targeting or doing this sort of banded approach gives us a pretty large improvement. And then it's sort of monotonically decreasing as we test more and more people. So you might say, well, this is not a very good benchmark. Why not compare to something like public data metrics, right? So a lot of countries at this time, they were reporting cases per capita, deaths per capita, and positivity rates, where you basically divide the cases per capita by the number of tests performed. And you can use this to kind of yardstick different countries, right? And so you can imagine, so then you would need exactly the same infrastructure that we created. So you need the same databases, you need to get the QR codes, you need to have the routing and things like that, because you're still doing targeting. The only difference is you're not doing reinforcement learning. So you're doing targeting based on some publicly reported metric that doesn't suffer banded feedback. And if you do this, we actually see that we still get a pretty sizable improvement. So compared to cases and deaths, we do about 40-ish% better. Compared to positivity rates, we do less better. We are about 25% better. But again, this is free. There's no financial investment here because you've already paid for the targeting. So just the benefit of using reinforcement learning is already getting you 25%. And just to rationalize this, the reason we did not want to use this kind of public data metric to benchmark different countries was because there's a lot of censoring going on that's country specific. So a lot of countries don't test as much because they maybe don't have the resources to do that. And so cases is a very systematically biased metric. And when you're using that metric to compare countries, it can be pretty unfair. Deaths is a little bit less censored because if you die, then it's kind of, then it still might not be attributed correctly, but positivity rate, which controls for the number of tests allocated, is kind of the least censored. And we kind of see that ordering here. So cases is, we do really well compared to cases. We do less well compared to deaths, and positivity metric, we only catch 25% more positive cases than we do with positivity rates.
Doesn't this assume that the chances that there's uniform subset of the population travel or go to Greece?
Yes, that is an excellent question. So I think that is exactly why we are still doing better, even though we have much smaller data than this. So the public data itself, I think, is not a good benchmark. And I'll talk about that in a little bit, because the population, like you said, that comes to Greece is very different from the population that's being tested in the country. So every country at this time, because testing resources were scarce, we're testing high risk, sick, typically lower socioeconomic status people. The people going on vacation to Greece in the middle of a pandemic are not those people. They're younger, lower risk, higher socioeconomic status. And so their risk profile is just completely different. So yes, that's a great point. And that's, I think, also contributing to why this doesn't do as well compared to reinforcement learning that's collecting the actual data that we want. And I'm going to argue that this is actually all still an underestimate because of gray listing. So if you imagine what happens in bandits, it invests a lot of effort exploring so that it can find high reward arms, and then it can keep exploiting that arms. But in this case, when we find a really high reward arm, we actually take it away, because if a country looks especially risky, we tell them not to come anymore, right? And that's the right thing to do for a public health perspective. But really, if you hadn't run the bandit, this is a conservative estimate of the counterfactual. So this counterfactual is a little bit harder to compute, so I'm not going to try to do it, although I'll give you the number that we get. So we gray listed 10 countries based on AVA's estimates over the summer, and it reduces both the prevalence. So clearly now they're getting a negative PCR pretest, so hopefully their prevalence goes down. It also reduces arrivals. So to estimate the counterfactual, you need to kind of figure out what's going on with both of those. So let me just show you one example. This is Malta. So we gray listed them kind of mid-August, so around this dotted line here. And you can see that the prevalence, so the actual, so that's the red line here, it immediately drops to, settles to a much smaller value, and the arrivals also drops about 40%. So this is why they don't like gray listing countries, but Malta is small, so they were okay doing that. And then we try to use like synthetic controls to figure out what the counterfactuals would be. And if you try to do that, then our improvement is about a little bit over 100%, but this is nothing like, this is not as clean as inverse propensity weighting. All I can really say is that it's an underestimate. Any questions about the results so far? Cool. So yes, I wanted to end with like one brief sentence about your point that the public data is unreliable. So one striking thing during the summer that we did, so we really wanted to try to incorporate both the lab data that we had and the public data. So here, prevalence, this is every point here is a country date pair. Prevalence here is what we are estimating using our empirical based method on the lab data. The y-axis here is the new cases per capita that's being reported by that country. So this in principle should be a straight line, right? You would expect that when you have high prevalence, you have high new cases and so on, right? And when it's low, both are low. But this correlation, I think, is more like zero. And I think this is exactly because of this point that the testing populations are just completely different and they're not representative of each other. Another issue is that there is a lag. So especially for the countries that have poorer infrastructure, like this is around the world, so not every country has the same resources. In some places, the case reports are delayed pretty significantly. So this is one example country where we saw, so our data is the green line and the public data is the red line. And we saw that they were spiking about a solid 2 weeks before they actually spiked in the public data. So this is sort of the value of doing in-house testing and doing reinforcement learning, because if we had just waited and relied on public data, we would have been letting these people in for about 2 weeks before we even realized that they were risky, right? So all this to say that we really need in-house testing and reinforcement learning can be useful. And that's all I had. Thank you, guys.
Thank you. Good job.
I have a few more questions, but I already asked several, so let's someone else go first.
So as usual, I have lots of questions too, but I have scheduled a discussion directly with Hamsa right after her talk. So Russ, go ahead.
So you throw away your data every 2 weeks, but couldn't you have some sort of like Bayesian method where you sort of use it, but becomes less reliable, and you look at the data, more recent data, and emphasize that?
You mean some sort of smoothing method?
Yeah, where you keep the previous data and you average it out with, or use a Bayesian approach, right? And just
Yeah, this is a great point. So we talked to some stats people and they told us that when the underlying process is smooth, then doing some sort of an exponential window or something like that makes sense. But because there are exponential changes, like these spikes are extremely sharp, they said it was more like change point detection. And in that case, what's better might be to keep a solid window. And we said, great, because that's easier to implement, so we'll just do that. But we haven't gone back and tried to figure out whether, which one reduced mean squared error. So that's a good question.
So I said I wouldn't ask questions and Matt's got his hand up, but relevant to Russ's question, how do you estimate that smoothness, that the world is, the world does what it wants, right? And the question is, where's the trade-off in applying a Bayesian method versus what you've done? How do you rationalize how you manage what is really noisy data anyway, right? That I haven't seen. So I think you're confident enough to be able to answer that, and we can discuss it more later, but I think that that's important.
I agree. And actually, so that's partly why when we started, we didn't even know what size window to use. And so we kind of punted it to our epidemiologist co-authors. But then we did do like a back test, like in the middle of the summer, where we collected enough data that we felt confident that we could use the data to estimate the window size. And I think the mean squared error minimizing window size was about 10 days. So it was pretty close to 14. So we kind of just left it at that.
But at least you know what it is, right? So at least you're aware of that sort of metadata to be able to inform the patterns you're looking for. Okay, thank you.
Exactly. But we didn't know what it was until halfway after the tool had been deployed. So initially you're just working with nothing. So you just kind of go off of some domain assumptions. I think there's a hand up, but I can't see your name, sorry.
Matt has a hand up. I can see that one.
Thanks, Randy. So as a reinforcement learning person, I am absolutely going to cite this because this is a great example of bandits actually being useful and not just making money for a company. So I know how to use reinforcement learning in Atari, and it's been a real challenge to go out and find good RL or bandit problems in the real world. So could you talk a little bit about the origin story? Are you a bandit person who found this problem? Did this problem find you? How did you find this great application for bandits?
I guess the problem found me. So basically, so I've been working on bandits for personalized healthcare for a while, but not in the real domain. I've been, I wanted to, but I haven't had the chance to. So I was very excited about this too. But my co-author, Kimon Drakopoulos, he's an epidemics guy. So he had a friend on the COVID-19 testing committee. And he asked them, like, what are you guys doing for testing? They said, oh, I guess we haven't thought about it, but probably random pull people off the customs line or something. And then he reached out to me and Vishal and said, like, hey, this is an interesting problem that seems to have some machine learning and optimization maybe in it. Do you guys want to build a prototype? At that time, we didn't think it was a bandit problem because we were going to use the public data to do the targeting, which doesn't suffer bandit feedback because that feels obvious. Then it turns out that that was a complete waste of time because I guess like Russ probably already saw like their unrepresentative populations, and you think there's still some signal in there, but I'm now convinced that there is no signal in there, and so we ended up switching to so I guess it was a little serendipitous.
Okay, thank you. I appreciate the story.
Yeah, of course. That said, I do think more people are interested in using these methods. We've talked to some clinical trial companies that are thinking about using bandits for some adaptive clinical trial testing. It's not like it won't be as real time as this because they have kind of, they have time to event outcomes, for example. So you want to do like survival analysis or estimate hazard ratios. So they're a little bit different. But I do think there's more and more interest. We've been working with Facebook on doing content moderation. So they're using bandits for that. I guess that's sort of like making money, but technically it's social good.
With meta now. I can talk. I'll point some papers where we've done something like that for. But let me go back to the question I asked earlier. Right, you had that picture where you did people you tested, people you didn't test, and obviously after they left the airplane, right, you can't test them then. But they were still tracking people who got sick later on.
Yes.
So those people, I guess it was the green people who were untested or teal, or
right.
Did you have any statistics about other people you didn't test? Here are the ones that got away, the ones you would have caught had you tested them. Did any statistics like that? Because that would show that false negatives was false positives.
Right. So we have some estimates. I would say out of all the infections that came in, we caught about 40% of them. So 20% was what we would have caught had we done random. And so we can get that up to 40%. But there's still a large number that are going out. I mean, given that we're only testing 18% of the population, we can't do better than that.
Of course, but still, you can still say, yeah. So given your constraints of how many tests you did, another question would be, how many tests should you have done? I know that's beyond your pay grade, but if someone said, if only I had twice as many tests, I could have saved, 3 more deaths, or I could have saved 100 more deaths, or
Yeah, we really asked this question so many times as policymakers. There's only one right answer to that, and their answer is always that you should have tested everyone,
well,
right?
of course, but
Even one death is not worth the price tag of having more tests. And that is what they're doing now, right? Now that we have rapid testing kits, they're testing every single person. So I think if they could have avoided the budget, there was no optimal number. If they could have avoided the budget constraint, they would have avoided it completely. Like, it's not like there's a nice curve. I mean, there is a curve, like there's diminishing returns to every additional test that you're doing, especially because we are targeting, right? So we get all the high risk people first. And so by the time you get closer and closer to 100%, like you're testing really low risk people. But I think it provides like, I mean, a lot of what Greece wants to do is tell visitors like, look, we're extremely safe. We are testing every single person, right? Right.
Again, great. That was a wonderful talk, and I'm glad you recorded. I got to show all my friends this because this is wonderful.
Thank you.
Does anyone else have any questions? Okay, if no one else has any other questions, I think we'll end it there. Thank you very much, Hamza, for your presentation.
Thank you for having me.